Okay, so the result that we are going to discuss today, and we will look at some applications of this in our next class. So, this was due to two scientists, Valiant and Vazirani. Okay, in fact, this is the same Vazirani who came to our department, I think last month, and this was in 86 or 87, I think 86. Okay. So what this, okay, so let me go ahead and state the result first, and then we will look at the necessary definitions and how the proof goes. So, what this result says is there exists a probabilistic polynomial time machine M that, given a formula, so it is a Boolean formula phi outputs a formula, let us call it psi, such that if phi is unsatisfiable, then psi is also unsatisfiable. Okay. And if phi is satisfiable, then with high probability. So, actually with probability greater than 1 over 8 n, psi has a unique satisfying assignment. So, basically given a Boolean formula in, let us say in CNF form, we will construct another Boolean formula which with very high probability will have a unique satisfying assignment if my original formula was satisfiable, and otherwise it does not have any satisfying assignment. Okay. So, this is the main technical lemma that we will prove today, and yeah, maybe Monday we will see some nice applications of this theorem. Because we can anyway amplify this, amplifying this is not difficult. Okay. So, note that this is, so that was actually going to be my next topic, but note that this is an algorithm which has a one sided error. Okay. So, it is like an RP algorithm. Okay. It is not technically an RP algorithm because it is not giving a Boolean output, it is outputting a string actually, but it is having a one sided error. So, it is very easy to amplify the success probability of this algorithm. Okay. In other words, how do you amplify success probability? So, we saw how to amplify the success probability of a BPP algorithm, okay, and that was kind of technical because we needed all these fancy bounds to get the result done. But if you have one sided error, then it is much simpler to amplify the probability, because what you do is you take, let us say, some t trials of this algorithm, and even if in one of the trials you get an accepting I mean if the machine accepts or if the machine correctly outputs a formula in this case, then you go ahead and output that formula. Okay. So, what is the probability that so the probability that it gives a wrong answer is 1 minus 1 over A10 whole raised to the power t, okay. And that can be brought to less than half or less than any polynomial for t which is at most polynomially large. So, that is not difficult to see. So, anyway, let me write that because I was planning to do so. So, what we can show is just to rephrase what I said in terms of an RP machine. Okay. Let M be a probabilistic polynomial time machine with a one-sided error of, let us say, some 1 over some polynomial p n, then for all polynomials q, okay, there exists a probabilistic polynomial time machine M prime such that M prime has a one-sided error of 1 minus error. So, so here I was talking about error. So, I will put this as 1 minus 1 over p n and this as error of 1 over 2 to the power q of n. Okay. So, even if you have a very large error, but still polynomially bounded away from 1, some inverse polynomially bounded away from 1, it can be reduced to an exponentially low error probability. And this is just by taking some polynomial number of runs of this machine M, and if the machine accepts in any of those runs, you accept. This is not very difficult to show. So, that is the reason why we consider this probability as sufficiently high success probability. Okay. So, any questions about the statement or you mean to say why is this? No, I am not saying this is easier to handle, but the point is that this has some nice properties, right. So, this formula has a property that with high probability it has a unique satisfying assignment. So, that helps us in certain cases. As I said, when we will see applications of this result maybe next class. So, we will see why this is a nice thing to have. But because this is not very, this is something not obvious, right. I mean you have a Boolean formula which can have any number of satisfying assignments, but you are claiming that without making any large error. Okay. So, with making only some small amount of error, you are reducing it to another Boolean formula which has only one satisfying assignment. So, that is quite a nice thing to have. What do you mean binary?
This function outputs a string.
This machine. Yeah.
So, how can we calculate this reduction in terms of set of binary?
So, you can look at the length of this, whatever is this string, you can look at the length of this string. Suppose this has some length n, and let us say this comes from a universe which has length m. So, So, you look at all functions from n to m such that if this is a formula which is satisfiable, then the resultant string will give you a formula which is which has a unique satisfying assignment with high probability. The resulting string will correspond to a formula, and if this is not satisfiable, then it is not here.
I am saying that in the polynomial time reductions, we said that this reduction goes from polynomial string to string.
Yes.
So we said that we can have in form of binomial function as this, that nth digit of this is 0 or 1.
N digit of what?
By formulating polynomial time string to string functions into binary functions. So
Correct. Yeah. So, you can formulate that as a So, no, but that I think you are talking about languages. So, languages you can think of them as Boolean functions. So, if you have a language, you can think of that as a Boolean function which maps to 1 if the string is present in the language and maps to 0 otherwise.
this is a reduction, polynomial reduction from P to string to Q. So
Now, what do you mean by reduction from a string to another string? You can only reduce from one language to another.
reduction is basically a function from string to string.
Yes.
So we can say this function like this. This function is a set of binary functions, which each of which gives
Correct.
a particular
One
state
bit.
of the answer.
Yeah.
So can we formulate this?
Yeah. Same way you can do this also. So, this machine, you can think of this machine as a collection of all those m functions, each of which is giving one bit of the string psi. Okay. But this is not just any arbitrary function, this is a randomized function in some sense. Okay. So, for the same string it can give a 0 bit in some cases, and it can give a 1 bit in some cases. So, it is not a deterministic function, because the machine itself is randomized.
The weight will be incorporated in each function.
So, if the concatenation of all those values satisfies this property, that the string that you get has this property that it has a unique satisfying assignment, then I think it will get incorporated.
Concatenation will have some property.
Yeah. Individually you will not get any data, I mean individually it is just one bit, I mean you want to look at the concatenation of all these. So, any other questions? So, okay, so here what I am saying is that, so suppose you have a machine M, okay, which has one sided error. So, if it is given a no instance, okay, so suppose you look at a string x which does not belong to the language, then it will output 0 with probability equal to 1. Okay. And if you give it a string x which is in the language, then it outputs 0 with probability less than 1 minus 1 over some p of n, okay, and it will output 1 with probability greater than, because this is not a good way to write this. Okay, so it outputs 1 with probability greater than 1 over p of n, and 0 with probability less than 1 minus 1 over p of n. Okay. So, that is what I am saying. So, suppose if you have a machine which has this one sided error property. So, here note that this probability is quite high, I mean it is giving a wrong answer with maybe a large probability, but it has the nice property that it is only a one sided error. So, here I am saying that from this machine you can get another machine M prime which has the same thing. So, if the string is not in the language it gives 0, but if the string is in the language, so this probability gets amplified to greater than 1 minus 1 over 2 to the power q of n. Okay. So, from 1 over p of n. So, think of p of n as something like 1/10. So, earlier it was giving only let us say probability 1/10 of success, but now it gets amplified to something very large for any polynomial q of n. Okay, and this can be achieved very easily by taking m runs and taking yes if any one of those runs give a yes answer. So, let us see what is the idea behind this theorem first, and then we will prove it. So, the idea is that so suppose okay, H is a family of pairwise independent hash functions, let us say from 0 1 to the power n to let us say 0 1 to the power k. Okay. So, what we mean by this pairwise independent hash functions I will come in a minute, but basically it means that all functions in this family distributes their output strings quite nicely in the set 0 1 to the power k. Okay. Then the probability that if I pick a random h here, the size of this set okay, is 1. So, this set is the collection of all those x's okay, such that H sends those x's to the all zeros vector. So, this probability is high. Okay. So, if I have this nice family of functions, then the probability that a randomly chosen function I mean for a randomly chosen function, the number of vectors which get mapped to the all 0 string okay, so that is equal to 1 has a high probability. So, this is what is the main idea behind this theorem, and this is what we will formalize and prove. Huh? No, I mean here n and k can be any general numbers. So, what this says is that for such a function on an average there is only one string which will get mapped to the all 0 string. Okay, so let us look at the proof, but before that let us look at some definitions. So, the first definition is regarding this hash functions. So, let H be a family of functions from n bit strings to m bit strings. Okay. So, then we say that H is a family of pairwise independent hash functions if for all x1 not equal to x2 in your domain, okay, and for all y1 comma y2 in your codomain, the probability that a randomly chosen function h has the property that h of x1 is equal to y1 and h of x2 is equal to y2 is equal to 1 over 2 to the power 2m. So, what this yeah, I mean if x1 and x2 are the same, then it implies that y1 and y2 are the same, right. So, does not make any sense. So, if I have 2 points, so what this says is that, so suppose if I look at this picture, okay. So, suppose this is my domain and this is my range, okay. So, if I pick any x1 here, okay, and I pick a random function here. So, what is the, I mean what do we mean when we say that this function randomly maps this x to one point in the codomain? It means that for any chosen y here, okay, h will map x to y with probability 1 over whatever is the size of this set, right. That is what it would mean. But here I want something more, I mean I am not only satisfied with getting this kind of independence, what I want is for any 2 strings here. So, if I have any 2 strings x1 and x2 which are different and I pick any 2 points in my codomain, the event that x1 gets mapped to y1, okay. So, this is my y1 and x2 gets mapped to y2, these 2 events are completely independent. So, basically the probability that one of them happens is 1 over 2 to the power m. So, because the size of this set is 2 to the power m and since they are independent, the probability is 1 over 2 to the power 2 m. So, that is what it means. So, if this happens, then I call such a family as a pairwise independent hash function family. So, one other way to interpret this as, okay, so just an alternative interpretation. So, this means that the probability that if I pick an h randomly from capital H, the probability that h of x1 is equal to y1 given that h of x2 is equal to y2 should be what? What do you expect it should be? It should just be 1 over 2 to the power m. I mean in other words, it should not depend on what this h is doing for this point x2. Okay. Yes. Not necessarily. So, if I allow y1 and y2 to be different, then I will rise, I mean I might have a problem, right, because the first y1 can be anything, but for the next value of y which is y2, you are only allowing it a set of size 2 to the power m minus 1. So, of course, that probability will decrease. So, it is not necessary that y1 and y2 are different, they can be the same. Okay. So, now the question is that does such families of functions exist? Okay, I mean, so this is just a hypothetical family. Is there an explicit way to construct such a family? So, the answer is yes, and I will just state this as a lemma and I leave the proof as exercise. Okay. So, let us define this family H. Okay, before I go to that, no, but see, what do you mean by all possible hash functions? You cannot, I mean what do you mean by a function being a hash function? That is not making sense, right. I mean you can only talk about a family being a collection of hash functions. If you look at the set of all possible functions, then clearly it does not satisfy this property, because if you look at the set of all possible functions from n bits to m bits, I am not sure, maybe it will be a family of hash functions, but see, ideally we want two things. Okay, ideally we want a collection of functions to be, I mean to have this property, and also we want this family to not have a very large size, because if I look at the collection of all possible functions from n to m, so that is huge, that is exponential in n. In fact, it's super exponential. So, what I ideally want is a small collection of functions which will have this property. So, yeah, probably you are right. If you take the collection of all functions, you can prove that it has this property. I am not sure, but should be true. But yeah, so the goal is to define a small set of such functions. So, that is what I am going to show here. So, what notation do I have? Okay. So, I will just use this notation h n comma m. So, this is the collection of all functions of the form h a1, a2 up to some a m, b1 up to bm. Okay. So, these are functions from 0 1 to the power m n to 0 1 to the power m, such that these ai's, so these are n bit vectors, the bi's are just a single bit, and h of say some a comma b. So, I am just denoting this as a vector of vectors given some vector x. So, this is equal to a dot x plus, okay, this is denoted as a 1 x plus b 1 comma a 2 x plus b 2 and so on up to a m x plus b m. Okay. And all arithmetic operations are modulo 2. Okay. So, what I am doing is that, so all these functions output a m bit string as follows. So, I take the dot product of a 1 with x and add the bit b 1, and similarly I do this for all the bits of my string h of x, and that is how I get these m bits. Claim is that if you have these vectors a 1 through a m, which are n bit vectors, and if you have some m bits b 1 through b m, then the collection of functions that is defined by this definition. So, this has the property that it is a pairwise independent hash function family. So, h n comma m is a pairwise independent family of hash functions. Okay. So, I will just leave this proof to you. This is the proof is little technical in nature, because you have to show that it satisfies this property, but it is not difficult. Okay. You can prove this. So, please try this proof. So, is the definition of this set clear? You look at all possible, yeah. So, let us say you look at all possible n bit strings, okay, for your AIs, and you look at all possible strings for these Bs. So, for one setting of these AIs and BIs, you get one function. Yeah, so this family will have 2 to the power m size, which is smaller than super exponential. Okay, so let's look at another lemma. So let T be a subset of 0 1 to the power n such that less than or equal to 2 to the power k, sorry, greater than or equal to 2 to the power k and less than 2 to the power k plus 1 for some k. Then the probability that if I pick a h randomly from this family of functions h n comma k plus 2, this set, the set of all x's belonging to T such that h of x is equal to the all zeros vector has cardinality 1 with probability greater than 1 over 8 n. So, if we can establish this lemma, then note that because I erase the theorem, but that theorem will follow from this, because then what you do is suppose we have suppose we know that this lemma is true, you can randomly pick these strings a1 through am and b1 through bm. Okay. So, that will give you a function here, and then what you do is okay. So, I just mentioned here, then you look the conjunction of these two formulas. So, given phi, okay, you define this function xi as phi and whatever formula will represent this following fact, that h of x is equal to the all zeros vector, or more particularly h of x is equal to 0 to the power k plus 2. Okay. So, this is how you define xi. Okay. So, now suppose if this lemma is true, okay, let us look at the two cases. Suppose if phi were to be unsatisfiable, then clearly xi is also unsatisfiable, because this is conjunction of some unsatisfiable formula and something else. So, this can never be satisfiable. But suppose if phi were to be satisfiable, okay, then what we get from this lemma is that if I look at, if let T denote the set of all satisfying assignments of phi, then we know that there is a high probability that a randomly chosen hash function will map all the x's, I am sorry, it will have the property that there is only one x which gets mapped to the all zeros vector. So, therefore, if I look at psi of x, okay, so this is equal to phi of x and h of x equals 0 to the power k by k plus 2. So, this will have just that one satisfying assignment with probability greater than 1 over 8 of n, because it is just that one string which will make this formula evaluate to true, and of course, that will make this also evaluate to true. Yes, so there will be multiple strings of phi x. So, there are multiple strings here. but only one of those strings among them will be able to make this equal to true with high probability, because that is what I pick. So, here I am saying that, so suppose this lemma is true. So, then this says that, so suppose I pick a set of strings, okay, such that it has the property that it lies between 2 to the power k and 2 to the power k plus 1, then this happens. So, what I do is that, so okay, so yeah, actually I skipped a step here. So, given phi, what you do is that you guess this function h, okay, by guessing these a1 through am and b1 through bm, and you also guess a number k, such that the number of satisfying assignments of phi lies between 2 to the power k and 2 to the power k plus 1. Okay, so that also, actually that was going to come here, but anyway. So, you also guess that number k, and then together with that you have the guarantee that T is the set of all satisfying assignments of phi, and only one string within T will make this evaluate to true with high probability. No, k is the k is this bound. So, 2 to the power k and 2 to the power k plus 1 are bounds on the number of satisfying assignments of phi. So, there is some k such that that gets bounded, right. Yes. What do you mean? So, think about it. So, let me just present the proof of this lemma. You can think for it for a while. We will come back to this later on. You want k to have this property. Actually, when we look at the proof of this lemma, we will need both these bounds. So, 2 to the power k should be smaller than t, and 2 to the power k plus 1 should be larger than t. So, that is, so we just guess one of them. Okay. So, what we will show is that, suppose we have a fixed k, okay, then the probability that this happens is greater than 1 over 1 by 8. Okay. But now, if I am also guessing this number k, the total number of possible choices for k is n. Okay. So, this probability gets reduced by a factor of another 1 over n, that is still fine with us. Yeah. So, what we will show initially is that, suppose we are fixing a k. So, suppose we know what our value k is, then we can argue that this probability is greater than 1 over 8. So, let us look at the proof of lemma 2 first. No, we will not use lemma 1 anymore. Huh? Yeah. So, we are just using the fact that this is a family of hash functions. So, lemma 1 only gives you an explicit way to construct such a function. So, when you write the actual algorithm for the theorem, so when you have to design the probabilistic polynomial time algorithm, how do you get the function? So, you guess all these ai's and bi's, and that gives you the hash function. So, that is where lemma 1 is used. Okay. So, first let us fix some x in 0 1 to the power n, okay, and let us also suppose that we know what our k is. Okay. Suppose that yeah, so we know what this particular k is. So, what we want to estimate is the probability for a randomly chosen h that this set has size 1. So, how can we alternatively write this event? So, this can be written as h of x is equal to the all zeros vector, okay, and for all y in t minus x, h of y is not equal to the all zeros vector. Okay. So, this is another way of writing this. So, there is only one x which gets mapped to the all zeros thing. So, let us try to look at how this can be written. So, this can be written as the probability that h of x is equal to 0 times, so using Bayes theorem, the probability that for all y in t minus x, h of y is not equal to the all zeros, given that h of x is equal to zeros. Okay, so, I am just for ease of notation just skipping this superscript of k plus 2 in all the vectors. So, this is by Bayes theorem. So, this probability is easy because this is a family of hash functions. So, a fixed x gets mapped to some fixed y is what? 1 by 2 to the power k plus 2. So, now the thing is that how do I estimate this probability? So, what is the complement of this event? So, the complement of this event is there exists a y in t minus x such that h of y gets mapped to 0 given h of x also gets mapped to 0. Okay. So, now we can use the union bound to bring that there exist outside. So, that is greater than or equal to 1 over 2 to the k plus 2 1 minus sigma over all y in t minus of x, the probability that h of y is equal to 0 given h of x is equal to 0. Okay. So, I am just using the union bound here, and what is this probability? So, since h is a family of pairwise independent hash functions, this is equal to 1 over 2 to the k plus 2 1 minus, I am just skipping a step here. So, this set has size p minus 1, okay, and this probability is 2 to the power k plus 2. So, this is greater than. So, now note that this probability is greater than half, right, because t is less than 2 to the power k plus 1. So, t minus 1 2 to the power k plus 2 is less than half. So, 1 minus a quantity which is less than half is of course greater than half. So, this is less than 2 to the power k plus 3. So, that is all. So, now the question is that, so I had done this entire thing for a fixed x, okay, but basically what I need is that, yes, yeah, this will be strictly greater than. Yeah. So, the thing is that how many x's do we have in t? So, basically what we want is finally to get this probability, and this is not quite the same as this, because here we are fixing an x. So, what we want is, what is the probability that there exists an x such that this entire thing happens, h of x is 0, and for all y in minus x, h of y is not equal to 0. So, how many x's do we have? So, we have a lower bound on the number of x's, which is 2 to the power k. Okay. So, therefore, this probability is greater than 2 to the power k times 1 over 2 to the power k plus 3. So, this is greater than 1 over 8. Actually, this is strictly greater than 1 over 8. Suppose we know what our k is, then we have this to be strictly greater than 1 over 8. But now, as I said that since we do not know what k is, I can just randomly guess a k at the beginning. So, that is why I get the extra 1 over n. Okay. So let us stop here today. We will look at the connection between this lemma and how we get the actual theorem maybe a little bit more at the beginning of next class, and then we will see application.